Dr. Merrily, chairpersons, thank you very much for this invitation to your meeting remotely. I hope I can tell you how cardiac ultrasound has developed and interest you over the last 60 years. The last 60 years have been really years of wonder in the development of cardiac ultrasound. And it's very interesting when you go back to the very beginning and look that its origins were in North Italy. A gentleman called Lazzaro Spallanzani, born near Modena in 1729, became a Jesuit priest. And he was subsequently a professor at the University of Bologna, Modena, Padua, and Pavia. He did the whole North Italian circuit. He had major experimental studies in bodily function, reproduction, and animal echolocation. Just two briefly to go into. In terms of spontaneous generation of life, he performed a very interesting study in that he left a broth culture out in the open air and observed microorganisms appeared on top. Now, his colleagues said this was a spontaneous generation of life. However, he then boiled the broth culture, covered it, and showed that this was totally due to organisms falling onto the broth. Indeed, he was also the first person to show that you need both sperm and an egg to reproduce an organism. In terms of animal echolocation, and this was 1793, he studied bats. And he took bats and put discs on their eyes and observed they could no longer fly in the dark. He then opened their eyes and put wax in their ears and showed then that they required sound to navigate. And he presumed that they sent and received a signal, a reflected signal, to allow them to identify objects. Now, nothing really happened at all till 1880 because we couldn't produce sound at frequencies we wished. And two brothers, the Curies, discovered piezoelectricity and used the developed crystals to create ultrasonic waves. So now we'd set the scene that we knew that reflected sound could be seen or displayed, and we could produce intonation. In 1912, Lewis Richardson suggested an ultrasound ranging technique could detect underwater objects. And indeed, Langevin in 1915 developed primitive radar. And radar means radio detection and ranging. And this was used to identify submarines in World War I. Now, the Americans took this over in the interwar periods, and by 1941, they had developed this into a technique to detect airplanes. Now, this was very interesting, but when you look at the clinical uses, it wasn't obvious. In 1937, however, Sergei Sokolov used ultrasonic waves as a means of detecting flaws in metals. And this became standard practice in, say, shipyards, etc. And in 1942, Floyd Firestone devised a metal flaw detecting device and measuring instrument that was commercially available. However, in 1941, Carl Dusek, an Australian neurophysicist, used ultrasound to look at the outline of the ventricles in the brain. He could see something, but concluded that this was probably not a viable clinical tool due to sound attenuation and interfering reflective waves. So he said, yes, you could see something, but no, it won't work. In 1946, Wolf-Dieter Keidel, a German physicist, used transmitted ultrasound to measure the cyclic variations in cardiac volume. However, he struggled to make his technique quantitative. Both Dusek and Keidel subsequently concluded that for theoretical reasons, reflected ultrasound could not be used as a diagnostic tool in the clinical setting. And indeed, if you were to ask a physicist who wasn't aware that we now use it, should it be technically possible and clinically useful, the answer would be no. So really, what happened after 46 to make it a technique we use in every day? Remembering that they said the immense technical problems compared to the crude, and I mean crude diagnostic possibilities, render any work in this field hardly worthwhile. So if I say that to you, you will stand up and leave the room and won't stay longer because we are not going to be able to use it. Now, this is where it gets very interesting. In 1953, two Swedish people came together in Lund. Hertz and Edler. And they looked at what they wanted to do. Now, Hertz was very interested in the clinical possibility of reflected ultrasound. And Edler was extremely interested in mitral stenosis and the practicalities of identifying people to send to the surgeons for open mitral valvotomy. Hertz read Der Ultraschall by Ludwig Bergman, and this was a theoretical ultrasound textbook. And he theorized that left atrial dimension could be measured. And this coincided with the clinical work of Inge Edler. They borrowed an ultrasonic reflectoscope used to detect flaws in metals from Kokum's shipyard in Malmo. And surprise, surprise, they detected cardiac signals. Now, Hertz's father was a professor of physics and a Nobel Prize winner, and was also a director of the Siemens company. Indeed, Hertz's uncle was a physicist as well, and he gave his name to the Hertz unit. So Hertz came from a family with very, very strong interest in ultrasound. He then went to visit Erlangen, the Siemens headquarters, where they were developing an advanced reflectoscope for industrial use. They asked to borrow it, and indeed, because his father was a director of Siemens, they were given one. And in 1954, after water bath experiments to validate A mode, Hertz and Engler proceeded to measure the thickness of cavities and cardiac walls. Edler then developed M mode echocardiography by stretching out in time the A mode signal and looking at it in that way. Interestingly, Hertz went on to be the father of the inkjet printer. So a tremendous amount of development done at that time in '54. Now, I've been very fortunate in the last 60 years to have met many of the people and been involved in some of the work that I'm going to discuss. But one of the most charming and modest men I ever met was Inge Edler. He only died 3 or 4 years ago. Some time ago, but to meet him was a sheer joy, a lovely man. I never met Hertz. Now, when we go on from '54, by 1977, and notice the time gap, 2D and pulse Doppler became available. Between 1970 and '75, 2D echo was developed, based really on transducer development and then data processing, but most of the development from 70 to 75 was transducer development. By 1982, 2D echo incorporating pulsed and continuous wave Doppler duplex scanning was as we know it. Now, in 1982, 2D transesophageal echo was developed from an original idea from the 1950s by Frazen, who used an M-mode transducer. And from the 1990s onward, we've had the developments of 3D echo, 4D echo, and tissue Doppler. So a progressive acceleration during those years. When we look at Doppler, and this is extremely interesting, Satomura in 1955 used a technique, almost pulse Doppler, to look at wall motion. By 1970, Light developed continuous wave Doppler for peripheral vascular use. 1972 to 75, 3 centers, the US, Japan, and France, independently developed pulse wave Doppler. In 1976, when directional information became available, Hackley and Holland developed continuous wave Doppler for pressure gradient estimation. Angelson in Trondheim combined pulse and continuous wave Doppler in the same imaging probe, and the development went on to '84, when Emoto really produced the first clinically useful 2D Doppler machine. And 1992, we were fortunate enough with Norman McDicken to develop Doppler tissue imaging. Now, I'm going to look at the different countries or different spheres of development now, because the history of this is fascinating. The French made a major European contribution. Franklin, peripheral arterial continuous wave Doppler, Georges and Pourcelot, non-directional continuous wave. In 1968, Bechamel put a transducer on a catheter tip and looked at venous and coronary flow. 1968, that's remarkable, but no one took it up as they thought it was an impractical tool. But all of these techniques were non-directional and were discredited as clinical tools. And in 1968, Kalmanson in Paris introduced resolved flow velocity recordings from pulse Doppler. Now, the problem in these early years was language. The French published only in French. The Japanese, who did amazing work, published only in Japanese. And the Americans, very cleverly, ruled the cardiac journals, and they did not look to any of these people to be involved. Publishing in those days was simply American journals, and every development was ascribed to the American who first wrote about it. But indeed, they developed quite a lot of things. Wild and Reed in 1952 examined excised hearts, and then Reed and Joyner wrote an article on mitral stenosis. Feigenbaum became interested in 1963, and he borrowed a neurologist's reflectoscope, and he could identify and describe what looked like a pericardial effusion. And in 1968, Feigenbaum and Dodge measured wall thickness and cavity dimensions, and he was the first to call the technique ecocardiographie. And very cheekily, in 1968, there was the first Indianapolis Echo course. And who should appear there to learn from Feigenbaum? Inge Edler. And it just shows the modesty of a man, that he was wanting to see where his technique was going. Another fascinating article, 1970, Eggleton mounted ultrasound crystals on a rotating electronic toothbrush to produce the first commercial 2D echo image. And very strikingly, in 1973, S.L. Johnson developed range-gated duplex scanning. This was an American machine, and it was of high quality. Now, interestingly, he went on to develop this further with a commercial variation of this. And this was seen by Hewlett-Packard as so advanced against their scanner that Hewlett-Packard bought the company and closed it down to stop this better scanner being developed. Fascinating. And in 1975, as I say, Frazen developed M-mode echocardiography. So in Japan, 1956, Satomura, an Osaka physicist, published a paper on blood flow in the limbs and in the eye using a mechanical vibration measurement, essentially Doppler echocardiography. And then 1957, he went on with Nomura and Yoshida to look at ultrasonic Doppler for inspection of cardiac function. This was non-directional resolved, but he could derive a waveform. Importantly, in 1958, they then went on to develop low-pass filters with simultaneous recordings of phono and ECG with the images obtained. And in 1962, Kater verified phase shift proportional to velocity, but said there was no directional information. And then in 1966, he developed a directional Doppler flow meter. So the Japanese, the French, and the Americans, and some of the English were running in parallel, but they really didn't read each other's work. And there we came to this 1970s, and then everything started to take off. We had pulse Doppler, high PRF Doppler, continuous wave, and 2D Doppler, which was getting near maturity. And when you look at the story here, we go to the 1990s, and we see that 92, with the development of strain rate, and from the 2000s onwards, the improvement in 3D echo, we are almost up to date. But these early pioneers contributed amazingly to what we do. 76 to 78, we saw all our standard things we wish to interrogate verified. Aortic stenosis, pressure gradient, VSD flow, ductus, pulmonary stenosis. Indeed, when you look at children's cardiology, and this is where mechanical sector scanners came into its own, by 1981, virtually every single condition could be identified by echocardiography, and using continuous wave and color Doppler, the severity could be estimated. And my own personal opinion is that in children's cardiology, apart from machine refinement, there has been no real new development since then. And the first book, Hatley and Angelson on ultrasound in cardiology, was written in 1980. Now, scanner development went on apace. Mechanical was best suited initially to pediatric cardiology. Adult phased array development lagged behind And this was due to a combination of transducer and display limitation. When we look at the original machines in the 1980s, they were using analog televisions to display the data, and they only had a frame rate of 28 per second. So they didn't need to collect data quickly because they could only display it with an update of 28 frames a second. Furthermore, transducer technology was poor. It took some time to correctly manufacture the ceramic probes and mount the crystals. And a major problem of the initial crystal ultrasound development of 2D, it became very difficult to solder the leads onto the crystals and get the information out of the scanner head into the system. But by the mid-1980s, we had a vast selection of things ultrasound could do. In terms of linear arrays, they are used for non-moving objects. And they're used obviously in obstetrics, in abdominal scanning, in head scanning. Cardiology requires sector scanning. And the sector scans went from 56, 128. You have enormous amount of crystals you could pack onto a transducer head. Although Frazen described ultrasound obtained from the esophagus in 1957, it was only in the early 90s, and a combination of Japanese and ourselves in Thorax Center developed this further. Peter Hanrath had been instrumental in giving the idea, and we went to Old Delft in Rotterdam, and they produced, via an Olympus gastroscope, they took out some of the fibers and replaced them by ultrasound cables and crystals that we could actually, at 2.5 megahertz, see a 2D image from the esophagus. This has been so far refined over the last years, we now scan in relative high resolution in 3D echo from the esophagus. So probe development, intravascular probes, everything, fantastic developments in probes. And then we come to 3D. Well, basically what we're wanting to do is see the heart in 3 dimensions and to resolve everything. And 2D arrays are difficult to manufacture, and frame rate remains the challenge. In terms of ultrasound machines, I would personally say that by the year 2000, the GE System 7 had every single facility and was totally diagnostic. And since then, we have, yes, improved imaging somewhat. We've refined the machines. We've developed handheld machines, as many large machines, but none of it has been a significant breakthrough at all. This is just technological. Myocardial Doppler possibly was the last different thing. And I can remember one day in Edinburgh going to have a coffee with Norman McDicken, and we were looking for a research project. And he said, "Hey, George, something interesting would be to go and look at changing the Doppler filters and to look at tissue rather than blood flow." And I show you the image here of the phantom we first used to verify that by looking at low velocities rather than the high velocities in the blood pool, we could measure flow, but not flow, we could measure wall motion. And we proved that this was absolutely viable. Doppler myocardial imaging, or tissue Doppler, has become a standard part of our tool. And indeed, in terms of this, most interest now is not on the Doppler insonation, but manipulating and measuring the 2D strain grayscale image. And by using this technology, we can measure many things, measurable indices of 2D strain. We can present the data in a variety of forms. We can look at different patterns. So you can see now that we're getting into complex analysis of the data. And this fundamentally is where the future lies. Now, if we look about 1990, we see the division in ultrasound machines. Acuson produced their first imaging machine from radiology in 1990. They developed it with parallel beamformers, and they, because of the complexity of the machine to produce image resolution and not image speed, they could produce very nice 2D grayscale 2D images, but it was impossible to drive the machine faster than 30 frames a second. And yet the ability on their display to do up to hundreds of frames a second. Similarly, with the implementation of tissue Doppler, Hewlett-Packard, who had kept their machine going from the 1970s without really modifying it, discovered that they couldn't change the filters in the machine without enormous cost, and this was not going to be viable. So Accuson and Hewlett-Packard existed in the 1990s, but looked very outdated machines. Other companies developed digital machines that were software driven. And this was the major advance, I think, in the 90s and 2000s, that we now had the capability of better transducers, better wiring to the machine, and digital machine software and analysis. But we still had to learn with all this new data what to do with it. Now, I just show very briefly the challenges, because if you were going to do real-time 3D echo, and you're going to try and take the data from your transducer, if you're going to do it in real time, you may require 18 gigabytes of semi-converted data. Now, this is a huge amount of data. If you look at the year 2000, in the University of Leuven, I think the whole need for the hospital was something like 20 terabits for a year, and this cost millions of pounds. Today, we buy 40 terabits and it costs almost nothing. So we now have the ability to store. And I can remember in the even 2000s, we were told, don't take 3 continuous beats. It's too expensive to store the data. So in summary, we now have storage. We now have transducer technology that works. Transfer is getting better. What should we do with the data? The other thing that has shifted on is how we take the data. We were used to multiple pulses being sent out and analyzed, but is there a better way of doing it? And Jensen et al. Described synthetic aperture imaging with 1 pulse. Many people now are working on ultra high frame rate deformation imaging. Up to 4,000 samples per second can be done in theory, and regional strain rates could be resolved in 3D. And these are 2 phantom images of limited diffraction beam imaging. What is the future of cardiac ultrasound? Well, machines will develop, but not in a huge way. Insonation will change, and we will use different insonation modes for different things we wish to look at. Very high frame rate imaging will become more and more available. As for research things, we can display things that the eye doesn't have the temporal resolution to see. But more than anything, we have to do better analysis. Quantification, early automated analysis algorithms work. But at the end of the day, I think you're going to hear my colleague, Professor Bynens, discussing artificial intelligence. And here we have a world of new possibilities. We will have improved 3D imaging, resolved strain and strain rate imaging, and we'll use these techniques to identify subclinical disease and monitor therapy in a way we can't at present. Nobody is going to describe mitral stenosis again for the first time. No one is going to measure the gradient across the aortic valve in a stenotic valve. These things are done and gone. But what we can do better is to acquire the data better, to understand the data better, and to use various algorithms involving artificial intelligence to give us a rigorous assessment of the data we've taken. Now, 60 years, and I've been there for virtually all of that time, and I think it's been one of the most amazing developments in cardiology. In 1976, I worked for Jane Somerville at the Heart Hospital in adolescent and adult congenital heart disease. And patients at that time were going to cardiac surgery to have the hearts opened on bypass to look and see if they were reparable. And if they were not reparable, then given the clinical indication, the chest was closed and the patient died. There should be no patient in this day and age who goes to cardiac surgery or passes through a cardiology clinic without having a full, appropriate cardiac ultrasound investigation and correct diagnosis. If these early pioneers had been given the opportunity to look 60 years forward, they would have been simply amazed at what we could do. But when we do it every day in the clinic, we don't tend to think of them. And I think this lecture has tried to put them back in their place. And the interesting thing was that it all started with bats in Emilia-Romagna. Thank you very much.